Uh, Let us start. Today, seminars of the algebraic geometries in East Asia is happy to introduce Dr. Đỗ Việt Cuong from Vietnam National University in Hanoi. He will say a talk on the moduli spaces of parabolic Higgs bundles on a curve. So please.
Okay, thank you very much for the. I would like to say thank you for the organizer to invite me to give a talk in this seminar. I'm very sorry because I'm sick, so I lost my voice. Okay, and for the inconvenience of because of some problem with my computer. So I hope everything is solved now and you can hear me better. So today I would like to give some talk about the moduli space of parabolic Higgs bundle on the curve. My talk has two main parts. The first part, I will give you some motivation why I want to study about the Higgs bundle. And I try to convince you that it's a very good subject and have a crucial play role in many branches of mathematics. And the second part, I give you some algorithm to calculate the moduli, the cohomology of moduli space of Higgs bundle. I couldn't hear the motive because I try to make a calculate independent of the characteristics of base field. So let me change to next slide. What is the first? I want to try to answer the question that what is the Higgs bundle on the curve? Yeah, for sure you can have a notion about Higgs bundle on more general algebraic variety like surface or something more higher range. But in this talk, I focus only on the curve. So here I fix some notation. It's a C here is a smooth curve. In fact, I1 is the projective curve and connected, but it's okay. So C here is a smooth curve of genus G, and I take omega C is be the canonical line bundle on C. So Higgs bundle is the pair of E and phi, where E is a holomorphic vector bundle over C, and phi is a Higgs field. It's a bundle map from the E to E tensor with the canonical line bundle. To motivate why we have this definition, I give you some remarks. That if you use the shared duality, you can see that you can take the Higgs bundle as a point of the cotangent space of moduli stacked vector bundle. This object first emerged in the works of Hitchin in 1987, and in the I think it's a collection of work of Simpson on the non-abelian Hodge theory. So why they call it Higgs bundle? Because the first Hitchin introduced, yes. The first Hitchin introduced the term Higgs field because there are some similarity with the object labeled in the way in the other equation of Gauge theory. You can something like the Higgs boson in the physics, and Simpson tried to shorthand this notion by Higgs bundle for the bundle together with the Higgs field. And in the next slide, I will try to convince you that the Higgs bundle is very interested in. Why? Because the Higgs bundle have a rich structure and play a crucial role in many different areas of mathematics, including gauge theory, Kähler and hyperkähler geometry, non-abelian Hodge theory, and most recently in mirror symmetry and Langland duality. In fact, for me, I know some words, some name of the theory, but in fact, almost of them here I don't know. In my application, I just keep in mind that I do the calculation for two main application. It's that if C is defined over the complex number, so the moduli space of Higgs bundle turn out to be diffeomorphic to the space of representation of the fundamental group of the curve. So in some sense that when the curve C defined over the complex number, by studying the Higgs bundle, I can have more knowledge about the theory of representation of fundamental group of some curve. Here is the projective curve. And if C is defined over finite field, so if C defined over finite field, we can have some problem about the counting the point on the variety. And the Ngo found some application of Higgs bundle in his proof for the fundamental lemma for Lie group, Lie algebra. So the start point is that the analytic description of the stack of Higgs bundle is closely related to space occurring in the study of trace formula. That is the start point of the proof of fundamental lemma of Ngo. Yes, so because I want to study Higgs bundle independent of the characteristics of base fields. So that's the reasons why I call in the first slide, I do calculate the motif. And what we know about the moduli space of Higgs bundle. In fact, if you agree with the three, my first three slide, okay, you know that the Higgs bundle is has very rich structure, geometric structure, but the knowledge about the cohomology of the moduli space has not yet been determined. We know only for the small rank, when rank equal 2 or 3 in the works of the Hitchin and his student Goten for a long time ago. But to generalize their work is it seems to be very hard, and there aren't any predict until now about the quite surprised. Tammerhausen and his collaborator Good de Gué Villegas is very hard to pronounce, managed to formulate a conjecture predicting the additive structure of the cohomology. He worked on the mirror symmetry and Langland duality, and he gave some conjecture to say something about the cohomology of moduli space of Higgs bundle. And in 2014, Garcia, Prada, Hilo, Schmidt gave an algorithm to calculate the motif. Yeah, the motif here is the same, means that independent on the Bayes or independent of cohomology theory we use. But this algorithm only works for the condition that the rank and the Ricci abundant are coprime. And after that, they use their algorithm to prove some specialization of the conjecture of Hausen and Gaudier Villegas. Yes, and my talk today, I will focus on the parabolic Higgs bundle. It's some kind of generalization of Higgs bundle. And why I want to do this thing, because uh, for the application in the trace formula, because you know that trace formula is that you can roughly speaking that trace formula you have two trace in application of trace formula, that you have two trace formula, and you want to use trace formula. I'm sorry, let me test again. Okay, so the first is trace formula is that's simply is that the equation between the two is the identity between the two parts. The first part is that geometric part is that you can have some kind of orbital integral and very geometric. And the second part is the spectral decomposition, give you some information about the representation of the automorphic form of the group. And to do to make a decomposition, the first question is that if you have a infinite sum, does this sum converge? Normally, it doesn't converge. So you need some truncation to remove some bad part in the decomposition. That's the reason that why the fundamental lemma proved by Ngo is not it needs some refine to make the trace formula work to bypass the conversion problem. So Lomong and Schroeder give some proof for the weighted fundamental lemma. And to prove this fundamental lemma, they use a public Higgs bundle, some kind of generation of Higgs bundle. And for the case of the curves defined over complex number, Simpson gives some relation between the modular space of public Higgs bundle with the space of representation, a fundamental roof. But for the punctual curve, that means that the curve now we remove some point, and now the curve is not smooth anymore, and they have a singularity. And to study the space of representation of the fundamental group of this curve, we need a public Higgs bundle. And I expect that when we work with the public Higgs bundle, we can remove the condition about the co-prime of degree and rank in the algorithm of AGEA, Prada, Hilot, and Schmidt. I expect that, but it blocked for a long time. The reason I believe that because the algorithm of AGEA, Prada, Hilot, Schmidt, we can do this method for N and D is not co-prime, but after we obtain a formula, we cannot get any information about homology. In the case of rank D and rank R and degree D co-prime, the space of the modular space of Higgs bundle fixed rank, fixed degree is smooth and quasi-projective, and the Tamahausen proves that it's the pure homology. So from the their formula, they can rid of, for example, the Horst polynomial, or they can rid of the dimension of the homology. And for the case of I and D is not co-prime, they get nothing. Okay, but when we work with public Higgs bundle, we have some kind called of condition of generic data, and with the generic data we have also the modular space is quasi-projective and pure. And to get the condition of generic, we don't need don't need rank and degree is profile. That's the reason why I believe that we can use public Higgs boson to remove some condition in the algorithm of Garcia, Hilot, and Smith. Okay, so I will come to the next slide to give you some definition of public structure to a vector boson and what is the public Higgs boson. So now we fix the say smooth projective curve, and now on the curve I marked some point P1 to PL, and I take E to be a holomorphic boson over C. So what is the public structure? We have E is boson, and now we attach to this boson a public structure. Is that a weighted flag? You have a flag, and on X vector boson, we give some number. Is we can call here it weight. This is not original definition of set theory. I do some cheating here. In set theory, every inequality here must be strict. But if you use the strict inequality here, when you define the weight on the sub-boson or the weight on the sub-Gaussian boson, you must to remove some weight, and it's very bad for my formula. So I use some cheating here. This cheat used in another paper of Polar, and he proved that we use it cheat is it doesn't change anything. So we don't have to worry about this thing. Okay, so now we have a definition of what is the strongly public map between the two public boson. If you write if you see the map like a matrix, you can see that this some kind of the upper triangle matrix, some kind of that. Okay, so we have something like we mentioned before in the first in the second slide about the Higgs boson. Now a public Higgs boson is a pair of public boson and a strongly public map, and we can collect we fix the rank, we fix the degree, we fix the weight. We can have moduli stack of Higgs public Higgs boson with fix the numerical data, and this stack is very best. And so we need like a GIT theory, we need some stable condition, and to define the stable condition for the public Higgs boson, we just add some for the normal is the slope is at degree over rank, and now for the public Higgs boson we add some thing control the weight, and we have the similar the condition for stable and semi-stable as in the case of vector boson. For sure here we have we add some map, so we need to some compatible condition that the sub-boson must be stable under the action of the map. That means that phi of f must send to f tensor with omega c of d and something like that. Sorry. And we can use GIT in the work of Okugawa. He proves that for D is called generic. D is a wet data. Generic when the semi-stable and the stable is the cosine. So he proved that this modular space exists, coaxial acid. And he proved that it's smooth, irreducible complex variety. And then he have a formula for the dimension of this modular space. Okay. And here you see that we need only the condition about the waste data it must be generic, and we don't require that R and D must be coprime. Here is N and D. N and N is rank and D is a degree, a coprime. So that's the reason why I believe, I explained before that I believe that I can use this work to remove the condition on the algorithm of AGEA and Hilot and Smith. I should mention a little bit here is that this modular space has an action of GM. It's very important for my calculation. I will try use this action to stratify this modular space to get some smaller piece, and I do some calculation on this smaller piece. Okay, so I will MDN and kappa D here. Fact D here is the main object I want to do some calculation. And you can ask me that you do your calculation over what? So I will explain you that where do I make the calculation. I want to calculate the cohomology of modular space. I want to so in the case the curve defined over C, that means that I want something like I want to know the dimension of cohomology. So I want to know the Horst polynomial, and more general, I want to know about the E polynomial. And for the K is is a finite field. I want to counting the point of the modular space, and the very best choice I think here is that we can use ring, a Gotenric ring, a variety of, here is a K0, a variety K. Is that you have but for some reason we need to add some, for example, you want to A1 class of A1 must be invertible, so you must add something like that to to this ring. So here I call the ring I use here is the K0 has a variety of K. It's some kind of completion of Gotenric ring. The reason that with this ring we have two maps to calculate the point and the map to the E polynomial. It depends on the application on C or on finite field. And I want also that my class of GLN must be invertible in K0 hat. Because we want to work with the Poisson stack, and our stack always have admit a stratification into locally closed substack of the form X divided by some group of GLN. Okay, So we have our we will make our calculation here, and we we want to calculate the classes of moduli space of public Higgs bundle in this botanic ring in some kind of modification. Okay, so a very naive approach to do my calculation is that using a variance of pitching approach to the cohomology. I reuse the approach of pitching for the case of rank 2. Is that he takes GM action on the moduli space of Higgs bundle, and he stratifies it by some small space, and each small space have relation with the fixed points of GM action. That is the icon here. Icon here is that the Bialy-Nicky-Biguda decomposition. That our moduli space can decompose into sub-variety. I note here is that the Fy plus. Such that Fy plus is some kind of fiber over some kind of cover over the disjoint strata of Fi, and this R5 bundle has this R5 bundle over the fixed point. Okay, and the second step in Hitchin approach that he tried to find a good description for the fixed point. And now in our case we have a theorem of Simpson. He says that in fact if we have a fixed point, we can explain it like some decomposition of public Higgs bundle, and we have some morphism between the public bundle in the directive sum here. Or I will try to restate this thing by the notion of the chain of public Higgs bundle. Yeah, in the next slide, I give you some public chain. So, public chain is that we have a collection of public bundle, and we have a map between the element of this collection. And for sure, this map must be strongly public Higgs morphism. And we claim that any public chain define a public Higgs bundle in the sense of Simpson, in the sense of Simpson theorem. And yes, for sure. Now public Higgs bundle, you have notion about stable, semi-stable. So we can define the definition for the public chain. That we say that the public chain is semi or stable if the underlying public Higgs bundle is semi or stable. And now we can define some moduli stack with the fixed numerical data like degree, like rank, and like width. And for sure, because here we have a collection of R public vector bundle, so we have the N here is at the collection of rank of X public bundle, as everything else is the same. And Garcia, Coutan, and Munoz prove that R5 fiber in the Bialy-Nicky-Biguda decomposition are all equal, and the number is a half of dimension of moduli space, the dimension of moduli space. So now we can do our now we want to calculate the class of moduli space of public Higgs bundle. And because this formula, we need only to calculate the public the class of public chain. Okay, and so it's the first reduced to our calculation. that now I don't do. I focus on the calculate the periodic on the class of periodic chain. And here I should mention that the pK roof of stack contain z power 2 power r plus on. So we can vary the stability condition on the periodic chain bundle. So here I give you some new definition about what is the alpha semi stable and alpha stable. This stability is very important in my calculation. Sorry. And then for sure, you can ask the question that why if I do my calculation on alpha stable stability condition, can I get back our first condition about stable? I said here is that yes, and for a good choice of alpha. For example, here, oh, I'm sorry. For example, here we have alpha is 0, 2, z, minus 2. We don't have m here. Is that some mistake, some typo here? And r multiple 2z minus 2. It's okay. Now I move to the next slide. So now we want to find or to calculate the periodic chain alpha stable, semi-stable. And the very naive approach is that we use the AGEA strategy to the convergence of moduli space of stable vector bundle. That's instead of we want to calculate the stable parts. So we will take on the moduli space, then we minus to the part the unstable part. Why we can do that? How we can do that? Because if you have unstable periodic chain, we can have a canonical Harder-Nagashima filtration, and we can use a Harder-Nagashima filtration to to calculate the unstable part. When you can know the unstable part, you know everything. You take everything minus unstable part, you get the stable part. Okay, so it's very naive. Then in the next slide, I will give you the how we work with the Harder-Nagashima filtration. So to make a calculation of Harder-Nagashima filter, we just we fix some type of Harder-Nagashima. Here we fix that some rank, some degree, some weight, and we writing, yeah, it's good. And then you take a forgetful map. No, I'm sorry. We just take a nature map from the we have a moduli stack. We have a moduli stack periodic chain bundle with type T. You can send to the product of moduli stack of subquotient of the Harder-Nagashima filtration. And we know that it is a smooth map of algebraic stack, and moreover, the alpha, the bundle, the fiber is alpha, and we can have we can do some calculation about the dimension, and here give you a formula for the Harder-Nagashima filter to the class a Porrick chain, but a rank smaller. So in some guy you have a inclusive formula, inductive formula, inclusive, yes. And to do the calculation of the dimension of fiber, we use the Riemann-Roch theorem, and we have some kind of the Euler characteristic here. We have, for sure, we have explicit formula, but it's very complicated. So let me don't mention about the formula here. So in some sense, we can do our calculation of Harder-Nagashima by induction. Okay. But we have some problem here in this approach. You want to take a total space, but this total space, this total stack is very big, and they do not. We can have any class in our ring define this moduli stack. So that means okay, you have something very big, you cannot calculate. So in some sense, maybe it doesn't work. So we need some kind of truncation. That means we remove something to have smaller, that we can do our calculation. And before I explain how we bypass this problem, I give you some very well behaved moduli stack that we can do our calculation directly without and we don't have any conversion problem with when we do this calculation. So yeah, here is some well behaved stack substack. We don't work with the global with the full stack. We work with the stack of Porrick chain, a blank N, liquidity with data D. But we have add some new condition here, is that the psi E must be injective. And in this case, we have an explicit formula for this class. In some sense, you can see that we can use like H modification approach to Hacker modification approach to calculate this the explicit formula, this the class of this the substack. Very different approach, and it's not hard, but quite long, and so I omit here. So I convince you that I have explicit formula for this substack. Okay, and now for the special case, when the rank, you see that the Porrick chain is that the rank can be varied. But now I see the special case that when the rank is the same and satisfy certain condition about the semi-stability, I wrote here. So I saw that in fact Porrick chains alpha stable in this case, in fact, it's a substack of the well-behaved substack I define over here. I can call that injective substack, for example. So, and when you take the subtext like that, we can see that this Porrick chain with this condition have a Harder-Nagashima filtration with very good condition here, is that rank of the subquotient in the Harder-Nagashima filtration have the same rank. So oh good, we can use the injective stack to make inclusive formula to calculation public share, to make a calculation for the classes of public chain when the rank is constant. Okay, so it at least we can use our very naive approach to do our calculation for very special substack. Here is that the substack of constant right. Okay, this is first one of the ingredient of our algorithm. Okay, so now I come to the circumvent our problem about the conversion. So we see in the title is a one crossing. So is that mean that we can think about to bypass the conversion problem? We can think about the alpha. And in the space, in the world of coarser moduli space, when we vary the stability, we have the process of one crossing. But here we do something in the world of moduli stack. So that's the reason why I make a quote over the one crossing. The advantage of the working with the stack is that we can avoid using the Jordan holder filtration. It's the advantage of the moduli stack. And for sure, here we like one crossing on the coarser moduli space. We have what is the critical value. So critical value is that we have some subchain have slope equal and slope is unequal in another value. So in some sense, you have in R n plus R in the space R n plus R. The set of creeping point is discrete. It's very easy to prove that. And now how and we can think about that. We calculate. We compare the classes of public chain for different choice of alpha, and we hope that this thing must give we some hint to bypass the conversion problem. And yes, we have a formula for this comparison. So because the R to power R plus on is very big, so we try to focus only some line on this space, and it's good enough for our application. So now I take an arbitrary alpha, and alpha is a critical value something, and I consider a line go through the alpha, and here here is just I take some delta, and I take a line go through alpha by the alpha plus t delta. So in this line we can we can talk about the we can cut this line to the segment, and inside the segment the stability and the classes of public chain doesn't change inside. Okay, and the problem is that what happened with the critical point and at the end of each segment, and I have some calculation. And the reason, the difference between the end of segment and the point inside is given by some formula related to Harder-Naga-Simhan traitor. And we know that the Harder-Naga-Simhan traitor, we can do we have some process, inclusive process to take a calculation. So in some sense, I know how to make, how to get a difference between the point inside and point on the S. Okay. Okay. So in the next slide, I do I give you some necessary condition for the existence of semi-stable Pareto chain. So that for fixed rank, for fixed degree, for fixed alpha, for fixed weight, the question is that, do we have a Pareto Higgs boson alpha semi-stable satisfy this condition, or have that invariance numerator or not? And this the provision give you that when, with what condition for n, for d, for alpha, for matrix d, this set is empty or not. Okay. I just give you that here is that the alpha semi-stable Pareto chains can only exist if we have some condition we wrote here. Okay, so if one of four condition if we have some problem with one of four conditions, that means that this Pareto chain does not exist. So we as the corollary, the class is 0 because we have empty set. Okay. So now I can move to our algorithm. So here the first step, we in fact here you know that when alpha is states, we want to do our calculation on a Pareto chain, holomorphic Pareto chain. Okay, with some origin stability condition. We modify by alpha semi-stable, but we know that we have alpha equal to 2z 0, 2z minus 2, etc. r 2z minus 2. So for our application, we need to do to compute the motif of modular space Pareto chain for this condition. Okay, so it's satisfied. Our application is inside this condition also. Okay, so the first step is that we have alpha we fix. We need to find some large t. I should mention here is that delta is arbitrary in our previous proposition. So we need to choose. Well, we need to do some well choose for delta, so that we know how we calculate the classes of Pareto chains for Taylor enough. In the previous slide, I said that we start with alpha. You go with the T last and last and last. Okay, and we cut this this line by segment, and for each segment, you know how to calculate the difference between the inside and at the S. Okay, so if you for T last enough, you can calculate the class by using the formula. You can go back to the alpha. I mean that's when on the line, you know how to calculate one point, and other point you can calculate via this point. Okay. Okay, so now how can I do with the choice of delta? Okay, so let's first we know that in the case of constant rank we have a explicit formula. So the first case he see here is that for the non-constant rank, that means that for some I and z we have ni and ng different, and this lemma give you this lemma give you how we choose delta to make the for t large enough the moduli space is empty. The moduli space is empty. That means that it conflict with some condition about the accident I gave you in the previous slide. I can choose that. Okay. And in the case n the rank is the constant. Okay, we did our calculate in above slide, so it's okay. Now the first step in we have alpha, we can choose delta such that for t enough we know how to calculate the moduli, the classes of moduli stack of some point. Okay, now we pass to the step 2. Step 2, we use the Cuong produce I mentioned before. The difference we know by Harder-Narasimhan. Harder-Narasimhan we can do some calculate by recursive formula. So by induction on the rank, I can give you the recursive formula for the public chain, a fixed rank, fixed degree, fixed weight data of alpha semi-stable with the condition that alpha si, alpha I minus alpha I minus 1 bigger than 2g minus 2. Okay, so we have a formula and we bypass the converse condition, and here is that the corollary of our algorithm is that we can have a formula and you can accept what kind of formula or you can do some explain about the formula you can get. So this is the corollary I mentioned here, is that the class of moduli space of public Higgs boson can be expressed in terms of L and the symmetric power of the curve C. One of these application of this formula is that if you have some formula on some characteristic, for example, Oliver Shipman gave a formula for the counting number of Higgs boson on the curve defined over finite field. But in his theorem, because of some problem of technique, he needs some condition about the characteristic must be bigger than something. And when we use this this application, we know that this formula must be true without the condition over without the condition over the characteristic. So in some sense, I can remove the condition about the character must be bigger than something in the theorem of Oliver Shipman when I use this algorithm. So this is the end of my talk, and thank you for the attention. Thank you very much.
Okay, thank you very much for the interesting talk. Any question for the speaker?
There is a question by Duke here.
No, I don't have any question. I just
So I have a question. Maybe if you the first one is you mentioned the stack of parabolic chains of ranks and but in the formulas you say it the formula lives on the quadratic ring of varieties. Maybe you should I don't know. Maybe you should replace the quadratic ring of varieties by the quadratic rings of stacks or something like that. This is the first question. Yes, let me explain my question. The question is in the slide 12, I can see the formulas of modularized space in terms of the p chains, the semisible, something like that. And this is a stack of the stack, but you say that the formula live in the concentric ring of variety. And
no. Okay. Okay.
Normally,
I said that my yes, I come back to the where do we make our calculation. So I said here that is the K0 hat is some kind of modification that bring quadratic ring of variety. It's not really quadratic ring of variety, because I want to have this formula. We have the equation stack x over GLN, and we want to have some kind of class divisor by class of GLN.
Okay.
And yes, for sure, like you said, you have some kind
yes,
of wood. Yeah.
Yeah. Okay. Your definition of quadratic rings is somewhat different from the quadratic ring varieties in the sense of conceiving.
Yeah.
Okay. Thank you.
Can I ask you in your last corollary, do you have the exact formula for modularized space of parabolic?
In fact, it's you see that we must to control many things like degree, like rank, like weight. So I'm sorry that I don't have explicit formula, but we know how can we do how can we make a calculation. For example, we can give this thing to calculator for computer, and it can make a calculation for genus smaller than 21. Yes.
Yeah, thank you.
For bigger, I don't know.
Okay, any more questions? Okay, and if no more question, let us thank speaker again.
Okay, thank you.
And the second talk for today is in the 10 minutes. Yes. We have a 10-minute break.